And our next speaker is Philip LaPorte from UC Berkeley, who's going to be telling us also about direct reciprocity and sort of and spaces of strategies in repeated games.
Okay, thanks. So yeah, this talk is called Complete Strategy Spaces of Direct Reciprocity. I'm a PhD student at UC Berkeley. Okay, so I'm going to be talking about some work that I recently that is recently published in PNAS, and this collaboration also includes Christian and Nicoletta, who you've heard from already. Okay, so the talk is about direct reciprocity, and this just means, the kind of point is long-run relationships are more interesting than one-time encounters. And you can have conditional strategies like I help you if you help me, and these actions can have downstream effects. And so my goals here is just develop some formal machinery to understand different classes of realistic long-run strategies and how they relate to each other, and hopefully shed some light on what strategy spaces should we use when we run evolutionary simulations and when our simple strategy is robust against complicated opponents. And so I say direct reciprocity, but really it's not necessarily evolution of cooperation. It could be any repeated game setting. Okay, so yeah, so we've heard about repeated games, but just this is my brief overview. So you could just think there's these building blocks, and a building block is just a simple interaction where players choose actions and receive payoffs. So here I have a sort of version of a prisoner's dilemma where you can imagine there's $100 or something, and players can either choose to split, and if they both split, then it just gets split 50-50. If one tries to steal, they get the whole pot. If they both try to steal, they get nothing. Okay, so just some setup like that. And then these building blocks are chained together in some chronological sequence, and the actions can be chosen based on the outcomes of the previous round. So this is what a repeated game is for me. So the framework is actually, for the results, is actually a bit more general. So in a repeated game, each round had the same structure, but in a stochastic game, the available actions and the payoffs, they can transition from round to round based on the actions that were played. So here's just a sort of simple diagram of stochastic game. So this is the payoff matrix. But then if the action profile played is down here, then you transition to this payoff matrix next. And there's no requirement that these all be the same size. In some cases, one player could have a ton of actions. The other player could have, a trivial action that does nothing. Yeah, stochastic game is a very, very flexible thing. And our results can be formulated in that setting, but I'm going to just present them in the setting of repeated games for simplicity. Okay, so how do we measure the long-run outcome of strategy? So we have these long-run strategies. How do we just assess how good they are? Well, I'll just use delta discounted payoffs. So that means just sum up the payoffs for every round, the expected payoffs for every round, but then it's a weighted sum, and the weights just decrease exponentially. So later rounds are valued less by some factor of delta, which is a parameter. Okay. And a long-run strategy for me is just a behavioral strategy. It just says, given the game history, what action am I going to play? And so the action is a probability distribution on some finite action set, AI, where I is the player. And so a history, this is going to be kind of important. A history is just a sequence of action profiles. So this is what was played in the initial round, and then this is the action profile that was played next, and so on. I just keep track of that, and that object is just my history. Okay. Okay, so when we study evolution of strategies, the big picture is just, okay, you have some kind of population, everyone's using a strategy, some agents play against other agents, and nature somehow selects long-run strategies based on their payoff somehow. So a high payoff should contribute to, you doing well and propagating maybe. The details are going to vary from model to model. So I'm not actually interested in any particular model here. I'm just trying to develop some conceptual frameworks that hopefully are relevant for a variety of models. Okay. So the problem with repeated games is that the space of all strategies is just too large to explore naively. You have an infinite set of histories. You can respond to them however you want. The combinatorial complexity just explodes very rapidly. And that's this is a persistent challenge for running simulations and for also studying things analytically. So for example, searching for Nash equilibrium strategies. And so what we typically do is we pick a convenient subspace to study. So mem1 here is what I'm calling the memory 1 strategies. They just remember the last round only. You could have memory n strategies. You could have reactive n strategies, which Nicoletta mentioned. There's plenty of other possibilities, which I will get into later. But a persistent concern would be that your strategy space could exclude relevant strategies. And I'll also say a little bit more about what I mean by that later. Okay. So many of you might be familiar with this result from Press and Dyson. It's actually not the main result of their paper. It's tucked in the appendix somewhere. But they say the shortest memory player sets the rules of the game. So what they mean is fix some n, and then imagine that one player is using a memory n strategy. So that player has constrained memory, and player two, the other player, might have a really long memory strategy. Okay, so they have way better capacity to remember things. They have some arbitrary strategy. Then what they proved is that, yeah, there's a typo there. So player two should be able to switch to an alternative strategy, which is also memory n, without affecting the long-run payoff of either player. So what it's saying is if you're playing against memory n, you might as well also be memory n. You don't get anything by being more complicated. You always have an equivalent representative in memory n. Okay, so what this means is that if a resident strategy in a population, which is memory n, it doesn't need to be tested against arbitrary mutants. If you want to know whether it's robust, you just test it against mutants within mem n, and that actually, every mutant has a representative there. And so we call memory n a complete space. This is terminology that we're introducing. Okay, and complete meaning exactly what's written above. Kind of every mutant against a memory n strategy has a representative also within memory n. Okay, so here's just the abstract definition, moving away from memory n. So just imagine I'm calling it S now. So player one uses a strategy from S. Here S is this subspace in blue. And then player two uses an arbitrary strategy Y, just somewhere out here maybe. And then the question is player two, using this strategy outside S, guaranteed to have an equivalent strategy in S, which results in the same discounted payoffs to both players? And if yes, then we say that S is complete. Okay, so this is what completeness looks like in payoff space. So this should be hopefully easy to understand. So it's just payoff space on the x-axis is the payoff to x, player one. On the y-axis is the payoff to y, player two. And then what we've done is we've fixed player one, x. So that's a fixed strategy within S. And then the other player just explores over all strategies. And each strategy gives a point in payoff space. And so the player that's ranging over all strategies, they can stay within the same restricted space S, and that gives rise to the blue dots, or they can venture outside of it, and that will give rise to the tan dots. And what completeness means is that the blue dots kind of fill out the entire feasible region. Okay. So these are for actual games. I don't have the details up here, but these are just for 2x2 games and simple strategy spaces. And so yeah, this is an example of what you might see if you plot payoffs against a fixed memory one strategy. And this is what you might see if you chose your strategy space in an unfortunate way. So one example of something that could give rise to that is if you were to look at reactive one strategies, so they just look at the last round only and only what the opponent did, and you chose a game that is not the donation game, not additive. Maybe it has a payoff matrix that isn't just the sum of a contribution from one player's action and a contribution from the other player's action. So for example, a snowdrift game, if you do a snowdrift game and reactive one strategies, you might get something like that. And so you'll notice that so X is fixed and Y is varying. So this is actually Y's best strategy amongst the ones that I plotted, and that's not in the space. So if you're just in the space, you actually won't really find the optimal strategy. And that's actually a problem for evolutionary simulations. It can artificially lead you to think that a strategy is stable, but it's just because you didn't try strategies outside. Okay, so the advantages of complete spaces, as I've kind of mentioned, is that if you're a resident and you're robust against all mutants in S, then you're robust against all possible mutants. Your simulation in S hopefully would yield more reliable conclusions. And if you're testing for Nash equilibria, you only need to check deviations within S. Okay, so now the question that I'm kind of working on is which strategy spaces are complete. So memory N is complete. That's a result of Press and Dyson, at least for the repeated game setting with discount factor 1. But it holds in full generality. And you could think of a memory N strategy by this kind of schematic. So a normal strategy maps histories to actions. A memory N strategy first maps histories to the N most recent rounds. So this is kind of a projection map onto the N most recent rounds and then maps that to actions. Okay, and then the question is what other strategy spaces might be complete? Okay, so as I said, a general strategy maps histories to actions. A memory N strategy has some kind of intermediate step where you're just looking at the most recent rounds. And then there's this kind of general framework of a factored strategy that was introduced by these authors in 2020, which is just to say you take the set of histories, you map it to some intermediate set, which could be sort of arbitrary, and then you map that to actions. And this first map from history from H to P is, you could think of it as like a selective memory. So H would be completely faithful memory, and you're sort of collapsing that in some way. And your strategy, your factored strategy would act based on phi of H, not H directly. Okay. So one way of thinking about these factors is that they're just partitions of H. So imagine you're playing a prisoner's dilemma, and you take all game histories H, and you sort them into a few bins. So you say, okay, bin 1 is just the histories that end in CC. Bin 2 is the histories that end in these three, and then, okay, maybe bin 3 is the empty history. And now instead of giving a probability to cooperate based on the history, you give a probability to cooperate based only on the bin. Okay, so if the history ended in DC or ended in DD, you kind of can't really see the difference between those two. You respond in the same way. And then, so your factor is this map that just takes histories and maps each history to the appropriate bin. Okay, and I'm writing P here for like partition. Okay, so the point of view that I'm taking in this talk is that a factor is just a partition of H histories, and these partitions or factors are associated with strategy spaces. So this first factor defines memory 1 strategies. So memory 1 strategies has basically 4 bins. They just care what the history ends in, the very last round. If it ends in CC, CD, DC, or DD, each of these bins gets a probability for cooperating next. There's actually another bin for the empty history, I guess what you do in the first round. And then this way of binning with just 2 bins defines memory 1 reactive strategies. It's simpler because there's just 2 bins. But there's many, many other ways to partition histories. And the more bins you have, the kind of larger the strategy space is and the more complex your strategy might be. Okay, so these factors, there's some mathematical structure that's kind of interesting. So some of them are refinements of others. This guy just has 2 bins. He only cares whether the history ended in CC. But maybe he refines it a little bit, and bin 2 is broken down into 2 additional bins. So maybe you split off this as an interesting outcome. History is ending in 2 rounds of DD. That becomes something you track. And then bin 3 is all the rest. Okay, so some factors are refinements of others. There's this kind of partial ordering on factors. But I'm going to return to thinking of them as maps rather than these partitions. So I'll probably stop talking about bins. But you can just think of this set P as a set of bins or bin labels, maybe. All right, so our main result is that if you have a factor for a repeated game, so I'm always going to assume that P is finite. And if your factor satisfies this following kind of interesting property. So let's say you have the history up to round T-1, and you know where to bin that. And then you're provided with the next action profile. So just using the bin and the action profile, can you figure out the next bin? That's the question. So I'll explain a little bit more about this property later. But if you satisfy it, then the space of 5-factor strategies is complete. So in other words, there's a lot of complete strategy spaces. And it's interesting to kind of dig into this condition a little bit more before I give examples. So this condition is called recursiveness. It was introduced in the 2020 paper that I mentioned earlier. And yeah, the interpretation is that if phi is your factor and it satisfies this property, then that means that you can update your memory incrementally when each new round is played. Okay, so there's this updating map that says, this is the bin I'm currently in. I add a new action to the history, and then I know what bin to place the new thing in. Okay. Another interpretation of this is to say that your strategy can be implemented by a deterministic finite state automaton where your states are the bins. So this is actually a very realistic condition on a strategy. I mean, we sort of think of strategies as being automata and people having memory that's able to be updated naturally. Okay, but just to, I guess, drive the point home, here's an example and a non-example. So an example is, let's say you're just storing the most recent n rounds. So here's your H, and then you're collapsing that, and then just to the most recent n rounds. So for each possibility of the most recent n rounds, you give a bin. And this is very updatable because if you know the most recent n rounds, you just add the new one on and you cut the last one off. Very easy to update. And that is recursive. Something that's non-recursive is if you're just tracking the second to last round. Okay, the problem is if you're just tracking the second to last round, and then the new actions are played, that's like 2 rounds ahead. You can't use that to update. If you want it to update, you need to know the guy in between, which you forgot. Okay. So you could make it recursive if you track a little more information. If you're tracking the second to last round and the last round together, then that becomes updatable. Okay, so here's one example of a factor. So this player is just tracking how many players cooperated last round in a prisoner's dilemma. So it could be either 0, 1, or 2, and those are the bins. And we would call a 5-factored strategy memory 1 counting, a counting strategy. And so a corollary of our theorem is that this space of strategies, which is 3-dimensional, is a complete space. Okay, so you could run, for example, an evolutionary simulation in it. The space would include strategies like win, stay, lose, shift, for example. Okay, so very concretely, here's how this completeness works. So one player uses some crazy strategy, which here is memory 1, but could be any memory. The other player uses something from the space, a counting strategy. So now this player who's counting stays the same. The other player can switch to a counting strategy, which I've computed here. This is for discounting 1. And then once that player switches into the same space, they get the same payoffs as they were getting before. So player 2 with some crazy strategy, which I guess isn't that crazy, always has an equivalent within the same space. Also, the result is constructive, so you can actually figure out how to find that representative. Okay, here's a second example. So let's say that your factor is just tracking player 2's most recent N actions. So you just single out player 2 for some reason, and you just track their most recent N actions. Now, I haven't said which player you are. I mean, you might be player 1 or you might be player 2. Now, if you're player 1 and you're tracking player 2, then you are what we would call reactive N. Okay. But if you're player 2 tracking player 2, you're what we would call self-reactive N. Okay. So you have to be a little bit careful when the factor is very asymmetric like that. And so I said that factors are associated with strategy spaces, but when you really in general, if you have an asymmetric factor, you're associated with 2 different strategy spaces, one from the perspective of player 1, one from the perspective of player 2, which may or may not be the same space. So in this case, it's asymmetric. In the memory N case, it's symmetric. So player 1 and player 2 are really using the same space. And so the main theorem that I mentioned, I said that 5-factored strategies are complete. But really, if you unpack what that means in this case, it means that if player 1 is using a reactive N strategy, then player 2, no matter what they're using, can switch to a self-reactive N strategy while preserving the payoffs. And vice versa. Okay. Actually, this connection between self-reactive N and reactive N, I was first told about this by Nicoletta, and that's what got me working on this project to begin with. Okay, so some additional notes about this result, just formally speaking. So I've been talking about these equivalent strategies, finding a payoff equivalent strategy. And what this depends on is it depends on the discount factor. It is sensitive to that. It, of course, depends on the strategy of player 1. And it depends on the subgame. So if you want to match payoffs, but you're only going to switch in the middle of the game, you need to know what happened before that. You need to know the subgame. But surprisingly, it doesn't depend on the payoff matrix. So the strategy that you're switching to, it doesn't need to, it will be the same for any game, actually. And the situation is a little bit different for best replies. So if you just want to find a best reply, you're just looking at your own payoff and you're optimizing that. You don't care about matching the other player's payoff or anything. Then it turns out you can find one that depends on, again, the discount factor and the strategy of player 1. It will, of course, have to depend on the payoff matrix because you're optimizing, you're finding a best reply. But you can find one that doesn't depend on the subgame, actually. And so there's an interesting almost duality between these two situations. So in the first case, your equivalent strategy depends on the subgame but not the payoff matrix. But if you're just finding a best reply, you can find one that doesn't depend on the subgame but does depend on the payoff matrix. Okay. So yeah, in conclusion, I guess complete strategy spaces is this conceptual framework that is important for evolutionary simulations and for finding Nash equilibria. And recursive factors represent kind of updatable memory structures, and they can be used to identify many complete spaces. And if you want to kind of learn more about this, you can read our paper or, of course, talk to me afterwards. And that's all I have, so thank you.
We have time for a question, and we're also going to take a 10-minute coffee break after. Oh, we'll do till 15. Okay, so we'll be back in yeah about yeah let's do about 3:50 I guess or 3:50.
So I have a quick question. A quick question. So the question is about mixed strategies. There's this idea of a learning reactive strategy where you recall not just the action you took, but own your own distribution of those actions.
Yes.
Is it correct or incorrect that does this you have not considered such histories in your whole entire project? Is that correct?
That's so actually okay. So if you're a reactive learning strategy, then are you speaking of reactive learning strategies or?
Well, just generally, it seems like the scope of your analysis is the histories are defined as trajectories of actions taken,
Yes,
not trajectories of distributions over such actions for which you might know for yourself.
that's right.
And the question, I guess, is like how much would change? Maybe you don't know this yet.
Oh,
If you allowed, at least for yourself, to remember what distribution you had over prior actions.
sure. I mean, my gut sense is that would make it even easier to kind of match what you need to, but I guess it depends. If you don't know what action you actually took and you only remember your mixed action, then the other player will respond in some way to that.
No, I guess I meant something that's both. Like you know what action you took and also
Okay.
you know. So you're adding information.
Yeah, I see.
But it might make it much like the complexity of finding the projection might be much easier.
Yes,
Yeah.
I could imagine it would be. Yeah, that seems right. But I haven't tried that. Yeah.
Can't your current mixed strategy be the value of the phi function? Right, if it's like a finite state, your state is your current mixed strategy. Well, that's I guess infinite state, but
yeah, so that's the problem. Like, yeah, that was so clever about the self-reactive learning strategies that you remember your randomization. So I don't know.
Yeah, so so I guess you're saying you're remembering the factor value. That's like the factor is your memory that you're keeping track of, and the factor value or the bin is in one-to-one correspondence with what your mixed action would be anyway.
yeah.
So in that sense, you do know your mixed action, I guess.
I'm tentatively making that argument. Yeah.
Yeah, I think that's true for our setup, but if you introduce things that are a little more complicated, like reactive learning strategies, then it becomes because a reactive learning strategy in principle could be using infinitely many different mixed actions over the course of its right. So that falls a little outside of what we're doing.